Okay, do we have everybody here? Seems like we have a sparse crowd. Oh, maybe that is everybody. Okay, a couple of things just to mention at the beginning. I know I've mentioned it in several classes leading up to this, but let me know if any of your classes from other teachers are either, whether it's CS or other, are either not meeting regularly at their defined time. If a class is supposed to meet 3 days a week, you should be meeting 3 days a week at the predefined time. Going for the whole class period, you should be having homework assignments. You should feel as close to a in-person class as you think is possible via online. There's been quite a bit of feedback that the university is getting from teachers that have converted their classes to basically attendance only, or everybody gets A's, or a class that's supposed to meet 3 times a week only meets once a week, that kind of stuff. And you know, while you're going to have some students that are going to be like, oh, great, less work to do, you're paying a lot of money for school, and this isn't ideal for anybody, and you should be getting your money's worth at least. You know, take an example of a teacher who's only teaching 1 day a week instead of 3, you know, because they said they have too many kids at home and they can't, you know, teach 3 times a week. Well, if you only showed up to work 1/3 of the time, you'd probably get fired. So, you know, make sure you hold your teachers accountable. Anything I let the administration know about would be anonymous and potentially not even specific to the teacher. It would be more to the department, and they would talk to the department chair and then have them deliver a global message to their faculty about make sure you're meeting at normal times, yada, yada, yada. Okay, so having said that, let's get into Mergesort. How did it go? Easy, hard, impossible?
The hard part was understanding how it actually merged, but after watching some like tutorials or like videos kind of explaining it and drawing it out is not that bad.
Okay. So the for the homework, we did the, let's call it the easier part of Mergesort. We did the merge step instead of the recursion step. But if we just bounce back over here, relaunch this and open our code. Oh, actually, we've been doing it. We have a Mergesort folder. Well, actually, I'll just do 300. I must not have actually clicked 300. That's the folder. Okay. Yeah, so here's our Mergesort driver. Let me close these couple of things here. So we make I just created a fake C array, 72143. We call Mergesort once. Remember, Mergesort's a divide and conquer algorithm, so it keeps dividing up over and over and over again. So here is Mergesort. We ask the question, well, we're printing out the portion of the array we're currently sorting, just shows us that we're going into the right places. If begin is not equal to end, this says if we're not looking at a 1 list, that means it's not sorted. It's not trivially sorted. So what do? We figure out the beginning and end of the first half, the beginning and the end of the second half, and we call Mergesort on the first half, and we call Mergesort on the second half. All right, now, once we return from the Mergesort, those 2 calls to Mergesort, we know we have a left half that is sorted and a right half that is sorted. The trivial version of this is when we hit two one lists. And a one list in and of itself is sorted, and another one list in and of itself is sorted. So what we need to do is we need to give ourselves a new array capable of holding enough memory or enough buckets to hold all the elements between begin 1 and end 2. So if begin 1 was 0 and end 2 was 4, that's 5 elements in there, right? So we need to have a, so if 0 to 4, 4 minus 0 is 4, plus 1 is 5. That's the number of elements we need to have in our array. What if it was between 4 and 8? 8 minus 4 is 4, plus 1 is 5. 4, 5, 6, 7, 8. So that's 5 buckets. So we need to have enough, we need to give ourselves a temporary array. So let me get some of these print statements out of the way here. So we're going to give ourselves a temporary array. So we'll say int temp, and temp is going to be of size n2 minus begin 1 plus 1. That's the number of buckets our temp array will hold. Okay, and we want to go through and we want to compare the elements inside of the first half to the elements inside the second half and pick a winner each time. So I'm going to create some new variables. We could reuse begin 1 and begin 2 here. So, but I'm just going to create new variables just to keep things separate. And let's see if did I name variables over here. My merge step. Oh yeah, I called it begin 1, end 1, begin 2, end 2. So we can actually just use those values. That's what we did in our example. So we'll just keep it with that.
For temp, could we also just do end minus begin, since the way the recursion works, it's, I don't know, kind of set that way, or do you have to specify end2 minus begin 1?
No, you could do end minus begin.
Okay.
That would work fine. Yeah, because that's the entire array you're working with. So in this case, begin 1 is begin and end 2 is end. So,
right.
Yeah. If you prefer that, that's fine. Okay, so this is a temporary array, but the important thing, the trick here for us is that this array has enough buckets to put all of our elements between begin and end in order. But this is always indexed from 0 to its length minus 1. Whereas we might not be working with bucket 0 and some number in the real array. So we need to make sure we copy back over in a correct way. So in any case, we could say, I know that I'm going to, here, actually, I'm going to do this. I'm going to say int size, let's say int length is equal to this. Just so we have that value. And we'll create our array of size length. That way we're not doing the tricky, how do you get the length of an array thing. We could, it'll work for this type of array, but might as well just hold the value.
Would length also be acceptable just to put end equivalent to it?
No, because end in the actual, we might be looking at buckets 4 through 8 in the array, and end would be 8 in that case, and that's only a 5 bucket array. So end only works if we are assuming that the portion of our array between begin and end always starts at 0. Begin is not necessarily 0 here. End is always going to be at least as big as begin, but it's not going to be, there's no guarantee that begin is 0. Begin, we could be looking at the right half of the list, and this could be 4 and this could be 8. So just saying the size of your length by setting length to end is not going to be accurate. If you're looking at between buckets 4 and 8 and you just say the length is 8, that's too big of an array. Does that make sense?
Yeah.
All right, so this will be the length. I'm just keeping track of that. That way I can use it for my for loop here in a second. So if we think about this, like I'm going through and I'm picking players for a kickball team, the number of players I need to pick, the number of winners I'm going to pick is length number of winners. So for int I is equal to 0, I is less than length, I plus plus. So that's the number of winners we're going to have to pick. Now we have two possibilities, well, three possibilities. We could either have begin 1 is off the end of its list, in which case we know the winner is begin 2. So we could say if begin 1 is greater than end 1. If that's true, then we know begin 2 is the winner by default. Else if begin 2 is greater than end 2, begin 1 is the winner by default. Else we have a battle. All right, and we know we can ask just these three, well, these two leading questions, because we know we're going to be placing the exact number of things here. We will not have a situation where both begin 1 and begin 2 are both illegal, because we have the perfect size temp array here. All right, so if begin 2 is the winner by default, we'll say temp at bucket I is equal to AR at begin 2, and then begin 2 plus plus. If begin 1 is the winner, we'll say temp at bucket I is equal to AR at bucket begin 1, begin 1 plus plus. All right, so this is if begin 1 is illegal, we declare begin 2 to be the winner for this pass. We grab that value, increment it. If begin 2 is illegal, begin 1 is the winner. Otherwise, we want the bigger of the two. So else if begin 1 or AR at bucket begin 1 is less than AR at bucket begin 2. If begin 1 is the winner, then we'll do the begin 1 stuff. Else do the begin 2 stuff. Okay, so this for loop will go through and pick length number of winners. So now what temp has, so now temp has the two halves of the list merged. We now have to copy those values back into AR. All right, so we are going to go from begin 1, well, from begin to end, including end. So for int I is equal to, actually I'm going to call it this, I'm going to say AR pause is equal to begin, comma, I'm going to show you a for loop where we can do two different variables. Temp pause is equal to 0. So we'll have two different counters here. AR pause is begin, temp pause is 0. Keep going as long as it doesn't matter if we say temp pause less than length or AR pause less than or equal to end, but we'll say temp pause less than length. That's the number of guys we're going to place. And then each time through we say temp pause plus plus, and we say AR pause plus plus. Increment both of those guys.
Would the problem with just setting AR equal to temp be that AR has like more unseen values higher up in the recursion process, or?
Well, yes, and if we use this as our example, let's go back one level. Well, here, let me just cheat off of 143. Okay, yeah, this would be a good example. So if this is AR here, and this is temp down here, and really if we're drawing the thing the correct way, this we say AR points to the beginning of this array, and we say temp points to the beginning of this array. So what you're saying is what if, so this is what AR is right now, up here, this guy. And this is what temp is. Temp is our array, and this is bucket 0, 1, 2, just to match up with our thing. So temp is 0, 1, 2, and we're trying to sort 2, 3, 4, these buckets here. All right, so you're saying after I have temp sorted, why can't I just say AR is equal to temp, right?
Yeah, I guess I wasn't following what we were sorting, so I'll keep watching.
Well, we're sorting all sorts of different places. So at any point in time when we call that merge step, we might be sorting. So in our example here, using just this picture, the first time we call that merge step, we're going to be sorting those two one lists. The next time we call it, we'll be sorting these two one lists. The next time we'll be sorting this 2 list and this 1 list. And then the last time we'll be sorting this, this 5 list. So merge is working on different portions of AR. The portions are arranged by begin to end. We use begin to end to tell us we're always passing this entire array around, the whole thing. We're just putting in a begin and an end to tell us which portion of this array are we currently looking at. And merge is working on that portion of that array. So in this case, by this example, temp is a 3 list, and it happens to be working with a begin of 2 and an end of 4, even though temp goes from 0 to 2. So if after we fill up temp with all our winners, temp is now the sorted version of AR between bucket begin and bucket end. If I just go ahead and say, AR is equal to temp like this, I've now lost my original array, and AR now points to this brand new smaller array that does happen to be sorted, but it's no longer, we've lost all of our data. So really what we need to do here is we need to say, copy bucket 0 from temp into bucket 2 from AR. Copy bucket 1 from temp into bucket 3 from AR. Bucket 2 from temp into bucket 4 from AR, because the portion of AR we were working with is between begin and end right there, even though temp is always going to be 0 to its length. That make sense?
Yeah, that helps. Thanks.
So that's why I'm keeping track of 2 different variables here in my for loop. And if you don't like putting multiple things in a for loop like this, that's fine. You can just define either AR pause or temp pause before the for loop and just use it inside and increment it yourself. But you can technically have more than one variable defined in a for loop, and you can change more than one variable in our for loop. So I'm going to keep track of where are we beginning in AR. We're going to be beginning at bucket begin, wherever that is. Where are we beginning in temp? Well, we're going to be beginning in temp at bucket 0, because because temp always starts at bucket 0, and AR will start in our example here at 2. So that's where begin was in that example. And then we're going to keep going. We can say temp pause less than length, or we can say AR pause less than or equal to end. Both of those are synonyms, because we know that temp holds the exact number of elements in it that we had to sort, because we did that right here when we calculated what length was. All right, so this will tell us how long we're going to go for. And then each time through, we'll increment temp pause and AR pause. So temp pause will go 0, 1, 2. AR pause will go 2, 3, 4. Where did I go? There we go. All right, so then each time through, what are we going to do? We're going to say AR at bucket AR pause is equal to temp at bucket temp pause. So we're copying the values from temp back over their original positions in AR, updating AR to be, updating that portion of AR to be the sorted version of itself. Okay, and we don't even need this else. We just had it in there to like let us know we had a 1 list, because if we are in this else here, that means that begin and end were equal to each other, which means that we don't do anything because it's already sorted. We've done all the magic we have to do to sort a 1 list, which is nothing. So we don't need an else, we just do nothing. Okay, so we call merge sort on our 72143. Taking all my print statements out. Looks like it. And there's our sorted list, 1, 2, 3, 4, 7. All right, so this was the homework. This is the merge step. Now, if you look at that, yes, it's several lines of code, but look at how simple the code is. You know, define a couple of variables, ask 4 questions, and then copy the stuff back over. So if you think about the logic of sorting here, the way that merge step works, the actual complexity of the sorting logic is pretty simple compared to like our insertion sort, where we have like the follower that bubbles up towards the beginning and all that stuff. So, you know, we've kind of spread the code out. We could probably write this a little bit more compactly, but as I keep stressing, write code in a very straightforward way. You should be able to talk through it as you're writing the code. In fact, I mean, I try to model that, you know, when I'm teaching it in class, but I'm not just doing this for, you know, the teaching perspective. This is probably how you should kind of have your own dialogue in your head as you're going through and writing the code. You're telling a story of how to solve this problem, so write the code that talks about each part of it. Don't go into some sort of trance where you're trying to come up with a really mathy looking solution to something or some trick to save yourself 2 lines of code. Very straightforward. This is how long my temporary array needs to be. Build my temporary array. I'm going to fill my temporary array with stuff. What stuff? Well, the winners between begin and end, where I know I have 2 half lists, and I have each of those sorted in and of themselves. So I'm going to be picking a winner from the first list and a winner from the second list. And if one of those lists has already had all their players picked, I'm going to default to the other list. Otherwise, I'm going to ask, who's the smaller value? And if you want to sort descending, you just change that guy right there. And now you have it descending. All right, so questions about merge sort there? Okay. So again, recursion is a really powerful tool. It's going to be one of those things that you're going to use, let's call it during your programming career, 5% of the time or something. It's not got a really common thing, but sometimes it's the right tool for the job. And I think what you will find, especially when you take the 470 class, I think that's next semester I put on the schedule, but so all of you should be taking that. Would be a good time to take it. I mentioned that we use a language in there where loops don't exist. So you have to do all your things that were loops, you have to do them through recursion. And because of that, you get pretty good at recursion in that class. But recursion is not that difficult to wrap your mind around if you get into this habit of having this, when I sit around and code, I don't sit here and talk to myself out loud, but the dialogue you're hearing me say, I'm saying in my head at some level. So when you say, oh, well, I am not dealing with a one list, so what do I need to do? Well, I need to sort the first half. I need to sort the second half. How do I sort the first half? I call merge sort. How do I sort the second half? I call merge sort. Merge sort knows how to sort a list. That's what he does. So if you kind of create that mentality of thinking about your functions as tools and understanding what they do, sometimes a recursive solution will reveal itself to you for a particular problem where you're in the middle of the problem and you're saying, oh, well, now I need to sort this again. How do I do that? Well, I just call this function again because that's what this function does. He sorts stuff. he does the job he's supposed to do. So try not to think of recursion as some sort of special case. Think of it as being, I have a tool that does something, and you might be in the middle of building a house using a hammer, and when you get to some room in the house, you might have to use the hammer again. For, in the middle of hammering, you might need another hammer to accomplish, I don't know, some task. You got to get one, you got to have a nail hammered in the middle of hammering one nail in before you can finish hammering the first one, something like that. And the right tool for hammering a nail in is a hammer. All right, so are we good on merge sort here? I'll go ahead and push that to GitHub. One of these days, I'm going to remember to set my GitHub username and password on this machine so I don't have to type it every single time, but that's okay. Okay. So now we're going to pivot back to Shunting Yard. And let me bring up Shunting Yard algorithm here. Okay, so I had everybody read through Shunting Yard a couple of classes ago. What does Shunting Yard do? What does this algorithm accomplish? What problem is it solving?
It separates from the executables and tries to basically it uses that to determine how the program can be executed.
Tell me more. It sounds like we're pretty off there, but it could be that I'm talking about the specific algorithm that we're talking about here. What problem are you trying to solve with Shunting Yard?
Sorry, could you repeat that? It's been a while since I read the code. I might be wrong. I mean, since I read
well, you were talking about executables and things like that. So, I mean, yeah, the Shunting Yard algorithm doesn't do anything with executables.
Sorry, when I say executables, I meant the plus, the time kind of thing.
Okay.
Basically, it goes through an equation I define as the x, the minuses, sorry, the plus, the minus, the multiplication, the division, that kind of thing. Which is what I meant executable. And then separates them from the numbers. it basically puts them into two separate lists.
Okay, and why are we putting it into two separate lists? So that's telling me how Shunting Yard accomplishes its task, but you haven't told me what task it's accomplishing yet. What does the tool called Shunting Yard actually solve? What task does it perform for us?
Basically,
If a hammer hammers in a nail, what does Shunting Yard do?
it identifies what an equation is telling the is that running basically for like a string.
Okay.
Basically, like it figures out what's being added. Basically, it figures out what is going on inside the function.
Okay, with the ultimate goal of doing what?
Adding, subtracting, dividing, that kind of thing.
Yeah, giving an answer, right? So it takes something that looks like this, and it does the math. But it does the math respective to orders of operation as well as parentheses. Make sense? So, you know, back in 200, I think, since my memory might be, we had a homework assignment called process expression, where we had to walk through a string and we were building up our individual numbers. Then when we hit an operator, we did something with that. But, you know, the whole idea was we had to assume that we were doing our math from left to right, regardless of what the order of operation was, where that's not how math actually works. Math actually works by saying, okay, I have a function, I have you know, an expression that looks like this. Well, I see parentheses, so I know I'm going to do the 2 minus 1 first. That's going to give me a 1. Now I see a multiplication, so I know I'm going to do 4 times that 1, which gives me a 4. And then I'm going to add the 3 to that gives me the 7. That's the correct answer, as opposed to, actually, this is kind of a bad example, isn't it? Because 3 plus 4, if I go left to right, 3 plus 4, actually, no, it's an okay example. So 3 plus 4 is 7 times 2 is 14 minus 1 is 13. So our process expression minus the parentheses back in 200 would have given us a 13 for this, when the correct answer is actually a 7 because of orders of operation. So what Shunting Yard does is it gives us an algorithm for having initially a string that looks like this, and turning this into a list of tokens, and then having those tokens go through the algorithm, ultimately performing the math that's in here with respect to order of operation. All right, and how does this accomplish it? So here is our, let me see if I can. All right, so it gives us kind of an example here. It doesn't matter what A, B, C, and D are. They're just some numbers. All right, so we're going to have this input Q up here that's going to have all of our individual tokens. So a number followed by an operator, a number, operator, number, operator, number. Parentheses aren't in this example, but they could be. There's an example down here, I think, that does have parentheses in it. It also has multiplication or powers. Well, whatever. We'll deal with that here in a minute. All right, so this is the queue we're feeding off of. So we want to process this guy. So we have a queue here called the input queue. We have our output queue here. And then we have this operator stack. So queues are a last in, or a first in, first out line. So this is like a line at McDonald's. This is another line at McDonald's. And then our stack is our stack is a last in, first out, push, pop, peek type of animal. All right. So as we start processing from our input queue, we see a number. What do we do with numbers? We just put them onto our output queue. So that A goes to our output queue. Then we hit a operator. What do we do with operators? I'm going to say this out loud right now. We won't see it for another step or so, but we're going to attempt to push this operator onto the operator stack. And we're going to see that this guy's going to have something in common with the towers of Hanoi, where we're going to have a couple of rules associated with pushing onto the stack, because only certain things are going to be allowed to push on top of other things. But right now it's the empty stack, so we'll go ahead and push the plus operator onto our operator stack. So now we look like this. We got the plus down here, we have A over here. Then we get the B. What do we do with the value? We just add it to the end of our output queue. So now we have A and B in our output queue. Then we get to our multiplication. We attempt to push this onto our operator stack. Now, we are allowed to push things that have a higher precedent in order of operation. So multiplication comes before addition. So as long as it has a higher precedent, we can push it on top of the plus sign. Okay? So we're able to push the X or the multiplication on top of the plus. So now our operator stack looks like this. All right, then we hit the C. C just goes onto our output queue. So we have A, B, and C there. Then we hit the minus. We attempt to push the minus onto our operator stack, but the minus is not bigger than the guy at the top. So what do? We will pop the multiplication. You know, we fail at attempting to push the minus onto the stack. Then we pop the multiplication off the stack. So there's the multiplication coming off the stack here. Then we attempt to push the minus again. Is the minus bigger than a plus? It is not. So what do we have to do? So it fails again. Then we pop the plus off and put it onto the output queue. So notice we have our multiplication and our addition on our output queue. Then we finally are able to push the minus onto our empty stack. We get our minus in here. Then we process our last value. We add that to our output queue. Now we're done feeding off the input queue. So once we're done feeding from the input queue, what do? We clear our op stack. So we just keep popping off our op stack and putting it at the end of our output queue until our op stack is empty. So ultimately, our op stack looks like this. A, B, C, X, or multiplication, addition, D, subtraction. Okay? So this guy, we can then do math with. So what we've done is we've ordered it in a, let's call it order of operation. Now, I'm gonna steal these guys here. Unless they give me a visual. Here they're showing you what the, oh yeah, this was the detail, the thing I was looking for. This one has parentheses in it as well. So we'll see how we deal with parentheses in a second. Let me come back to that. But for right now, let's think about how do we process this math? A, B, C, X. Why do I keep calling it X? That's terrible. Multiplication, addition, I guess I'm looking for it to be a asterisk. Multiplication, addition, D, and minus. So I'm gonna put that into a slide here for us. ABC times plus A, B, C times plus D minus. Okay. So now the question is how do we do this math? Because now I have a queue that has all of my tokens in, let's call it the correct order to do the math. So what am I going to do? I'm going to use a stack to do this math. So I'll put a little, use a stack to do the math. Oh, yeah, I was gonna fix it. Okay. So this guy is gonna be my stack. And I'll make it the top here. And remember, we push and pop from stacks. So I run into an A here. Since it's a value, I'm going to push it onto the stack. Then I run into the B. It's a value. I'm gonna push it onto the stack. Then I run into the C, it's a value. I'm gonna push it onto the stack. Then I run into the multiplication. And what does multiplication do? Well, multiplication consumes two parameters, the C and the B, to multiply them together. So just in our example here, I'm going to replace these guys with 4, 6, 2, and 3. Okay, so let me just go and redo this real quick. So we pushed a 4 on, then we pushed a 6 on, then we pushed a 2 on. Then we hit the multiplication, and the multiplication requires two numbers to work. So we're going to pop the top two things from the stack. We're going to consume the top two things from the stack. We're going to pop the 2. We're going to pop the 6. We're going to apply the multiplication to it. So 2 times 6 is 12. And then we'll push that result back onto the stack. All right. Then we hit the addition. Addition takes two parameters. So we're going to consume the first two things in our stack. So pop, pop. Add 12 and then perform this operation. So add 12 plus 4, which is 16, pushing that result back onto the stack. Then we hit the 3. Then we hit, and so we push a 3, it's just a number we push it onto the stack. Then we hit the minus. Minus says we need to consume two elements from the stack. So we'll consume the 16 and the 3. We'll subtract the 3 from the 16, giving us a 13, pushing the result back onto the stack. Now we have finished processing our Q here, and our final answer is at the top of the stack. So you see how we used the stack to do the math there? So this guy, our output Q, it put the stuff in the correct order for me to go through and use a stack to perform the math. And then that stack allowed me to have the final value after I performed the math sitting at the top of the stack. All right, so we need to do several steps here. On one hand, when we're thinking about shunting yard, if we have something that looks like, 1 plus 3 times 2 minus 4 times 6 or something like that, we need to get these guys into individual tokens. So we want to go from that to 1 plus 3 times 2 minus open parenthesis 4 times 6 closing parenthesis. We want these as individual tokens. So we can think about these as being like comma delimited if you want to think about that. We're going to have them inside of a queue that we'll create. All right, so we need to turn a string into a queue of tokens. So this is a queue of tokens. Then we're going to need a output queue. We're going to need an operator stack. So that's going to be our given information, those things. Then we're going to perform shunting yard to get a let's call it an output queue solution. Finally, process output queue using a stack to do the math. All right, so that's our process. This is our raw ingredients, and we're going to then manipulate them into this format, then create our, so this will give us our input queue. So this is called our input queue. And then we'll have an empty output queue initially and an empty operator stack. And we'll perform the shunting yard algorithm we just went through, which will fill up our output queue. And once we have that, so once we've performed shunting yard initially, we will have our output queue filled up with stuff. Then we can use a stack to go and do the math. Okay? And that's this last piece here, process output queue using a stack to do the math. All right, so before we go on, are there any questions about how shunting yard works? Because the first thing we need to do before we can start creating a solution is we need to understand the problem. So what questions do we have about about the problem?
How are we going to be able to know like which operators have higher priorities over others? Like parentheses, multiplication, division, stuff like that.
Yeah, so down here in shunting yard, I mean, this is normal math anyways, and most of it's stuff we're already familiar with, except probably maybe we don't think about powers. In fact, in our solution here, we're just going to ignore powers, so we don't have to treat it as a special case. But we know multiplication and division are more powerful than addition and subtraction, right? But multiplication and division are equally powerful to each other. So that means we do them from left to right when there's a tie. Similarly, addition and subtraction have so using this guy, multiplication and division have a power of 3. Addition and subtraction have a power of 2. And taking something to a power has a power of 4. It's the most powerful of them. We always do those first. We always resolve things to a power first, other than things in parentheses. Okay, so this guy, we would say 1 minus 5 is -4, or -4 squared, and then take that value to the 3rd power before we even do the rest of this math. So then at that point, we would say left to right on the 4 times 2 and so on and so forth. Okay, so this isn't something made up by shunting yard. This is just how math works for orders of operation. But in the algorithm thing here, they gave us a little chart. One thing to look at here. So let's just quickly look at how a parenthesis is dealt with for opening and closing parentheses. So if we're processing this string, well, this is already in token format, let's say. So we already have this. This is our input queue. So we'll take the 3 goes to our output. Then we get the plus goes to our, in fact, here. And just because I said we're not going to work with the powers right now, let's just keep it relatively simple. It's not hard to deal with them. It's just a little bit of a twist and relatively unimportant for the exercise we're doing. All right, so let's say I have something that looks like this. We're going to have our input queue, which currently looks like that. We're going to have our output queue, which currently has nothing in it. And then we're going to have our op stack, which currently has nothing in it. All right, so as we process through this, we're going to burn that 3. And what do we do with it? It's a number. We just put it onto our output queue. It gets put in line. All right, then we hit
So
the
you
plus.
were,
Go ahead.
sorry, you were specifying like stack, you use push, pop, things like that. You use that with queues as well though, right?
Queues have officially the functions for a queue are enqueue and dequeue. So this is add to end. This is remove from front. So those are the they're akin to push and pop for, so their version of push is NQ, which says add to the end of the list, add to the end of the queue, add to the end of the line. DQ removes from the front of the line. So it's a first in, first out, normal line like McDonald's. But
So are those, go ahead.
yeah, so these are the official terms for what queues do. But if you think about this in terms of a linked list, NQ is the same thing as add end. DQ
Okay.
the same thing as remove front. It's just a fancy name for that move.
So for queues, we just use the same tools we have for linked lists.
We use the same tools we have, but you can think about them like we've done with stacks. So stacks and queues are simplified versions of linked lists. When we wrote a linked list initially, we had this, this monster thing that knew how to do everything under the sun, add to the front, add an index, remove an index, blah, 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 all this stuff. Where a stack and a queue, they don't need to be that fancy. They both need, a queue just needs to be able to remove stuff from the front and add stuff to the end. That's it. That's what that tool does. So it's a much simpler, well, it's a less featured thing, but it serves its purpose whenever we need a queue. Similarly, so with a queue, we would not be able to get something at bucket 3 in the queue. It doesn't make sense for a line. If you're at McDonald's, they don't just wave the third person in line forward and just let them skip the line. Or at least that's not the way it's supposed to work. So a line at McDonald's only needs to have an end where you can get into the line and a front where you can order and get out of line. That's what that tool does. So it's a much simpler version of a linked list with a cut down set of features. Same thing with the stack. You just need to be able to add to the front and remove from the front and look at the front. Those are the only 3 things that a stack needs to be able to do. So if you think about sitting down, just writing that real quick, you don't need this, real beefy linked list thing that knows how to do 4 million things, because you only need a couple of those features to make stacks and queues work. But to your point, if you go back to your original linked list, if you were writing a queue, NQ is the identical logic to add end. DQ is the identical logic to remove front. You don't have to change it at all. You just don't need the other things for a queue. Does that make some sense?
Yep.
Okay, so as we start processing through this guy, we burned the 3 from our input queue and just put it onto our output queue, because that's what we do with numbers. Okay, then we hit the plus. What do we do with the plus? Well, the plus is an operator, so we try to add it to our op stack. And in this case, the op stack is empty, so we are successful. Then we hit the 4, so we NQ that, add it to the end of our output queue. Then we hit the multiplication. We try to put it onto our op stack. Op stacks are, and we try to push it onto our op stack, because this is a stack. And since multiplication is more powerful than addition, we are able to push it on top of our op stack. So notice that I pushed it on top instead of NQ'd it onto our output queue. Then I hit a number, we NQ that. Then I hit division. Now, division is not more powerful than X. So I try to push it on here and I fail, okay? Because these 2 guys are tied. Division and multiplication are tied with each other. So what do? I'm going to pop off op stack and NQ that guy. Then I'm going to attempt to push division onto the op stack. And is division more powerful than addition? It is. It's pretty funny. I have to copy that because I don't have that key on my keyboard. So that's unfortunate. So we have our, now we burn this guy, we put it onto our op stack. So now we're looking at how do I handle parentheses. Okay, so this is, now we can make a guess here. So whenever we run into something that's a parenthesis, we know that this is the most powerful thing, right? So a parenthesis tells us that it is this should happen first, regardless of order of operation. All right, so they run into the opening parentheses. So this is their input queue. So they hit the opening parenthesis. Actually, hold on, where's my, here's my token. So here's the next token of my input queue, open parenthesis. What do? We push it onto the stack. Now, we're gonna say again, we're going to try to push it onto the stack. But to get that opening parenthesis onto the stack is very easy. He just goes onto the stack. He's more powerful than everything. All right? So we don't have to check, are you more powerful than division? We can just say he has the power of 1,000,000. He's more powerful than all the other ones. So we push him onto the stack. So now he's at the top of the stack. Okay, then we hit a number. What do we do with numbers? We NQ them. Then we get to the minus. What do we do to the minus? We push it onto the stack. And this is where things get a little weird. Notice I said that the parenthesis has like a superpower, like it's 1,000,000, let's say. Well, and we've previously had the rule that you could only push something that's more powerful on top of something else. And we look at minus as being very weak, but minus can go on top of parentheses. So parentheses are treated as a special case. So we burn the minus, and we are able to successfully push that on top of the parenthesis. Then we hit the 5. What do we do with the 5? Well, we NQ it. All right, so now we hit the closing parenthesis. Now, the closing parenthesis doesn't get put anywhere. Instead, it's a call to action. It tells us to do something. What does it tell us to do? It tells us to pop from our output stack until we hit the opening parenthesis. So we just got this guy. So it says we're going to pop from this until we hit the opening parenthesis. So we're going to get the minus. Then we're going to pop again, and we have our opening parenthesis. We don't add that to our output queue. We just know that we've finished processing the closing parenthesis. So that guy can just, hello, I'll just do that. That guy can now disappear, but notice I didn't put him anywhere. So closing parentheses do not go anywhere. They just are a call to action that says, clear out our op stack until we get to the corresponding opening parenthesis. So we were able to grab the minus, and then we burned the closing parenthesis. We didn't put it anywhere. Just as soon as we popped the closing parenthesis off of the op stack, we knew we were done. All right. So now we're done with our input queue. So what do? We clear our op stack. So we'll pop. I need to copy this again. And then we pop again. So now our op stack is empty, and here's what our output queue looks like. And now we can do the math with this. So if we call this guy the math stack, we have a 3, we push it on. We have a 4, we push it on. We have a 2, we push it on. Then we hit multiplication. Multiplication says to do what? It says that we are going to perform an operation. This guy requires 2 parameters, so we pop, the two parameters, perform multiplication, 2 times 4 is 8, push that result back onto the stack. Then we hit a 1, push it onto the stack. We hit a 5, push it onto the stack. We hit a minus. What does minus say to do? It takes two parameters. It says take the 1 and subtract from it the 5, giving us a -4, pushing that back onto the stack. Then we hit the divide. 8 divided by -4 is what, -2? Push it back onto the stack. -2 plus 3, plus takes two parameters. We do the math, push it back onto the stack. There's our final answer of a 1.
Wow.
What's up?
Wow.
So we see the power of stacks, even though they're very simple. We can use stacks for all sorts of different problems, and they're really simple to implement once you understand linear linked data structures, because we don't have to implement the 4 zillion hard linked list things like add at index and remove at index and stuff like that. It's add front, remove front. Stacks are super simple and super powerful. In fact, our entire operating system is based around a stack. The way processor management works, it uses a stack. Okay, so any questions on the shunting yard algorithm in terms of how it works? Again, we have to understand the problem before we can start writing code.
I have more of a question about like C++. I know there's a generic linked list that we're not allowed to use yet, but in the future when we're actually in industry we can use. Is
Sure.
there a stack and a queue version of that as well?
Yep. Pretty much every language will have those.
Sweet.
Or what they'll have is they'll have a linked list class that has the push, pop, and peek functions and the NQ and DQ functions as part of it. But even then, so like for instance, in Java, the linked list class in Java supports push, pop, peek, as well as Q and NQ and DQ. But then they also have stack and queue classes, which are abstractions of linked list that only have those features. All right, so let's see what we had already written before we switch to recursion awesomeness.
Wait, I have a question dealing
Yep.
with sort of like, so the procedure you laid out just now is kind of like what you want us to do with the code here, basically.
Well, right now I want you to understand what we just did.
Yes.
And then the next couple of homework assignments are going to involve doing stuff with this.
Okay. So we're slowly building it up.
Slow-ish.
Slowish.
Not slowly. Not slowly.
Sorry.
I'll probably give you a portion of it for Thursday and then the rest
Okay.
of it for Tuesday.
You don't want to throw us into the lion's den yet, I see.
Yeah, I'd rather ruin your weekend than ruin. I actually kind of want to ruin both. You need something to do. You're at home. You can't go outside. So yeah.
We have other homework assignments.
From what I'm hearing, some of these teachers aren't giving other homework.
Now in my classes, there aren't. They're giving plenty of homework there.
Well, good. That's the way it should be.
Why should we be punished?
You should be just as tormented at home doing your schoolwork online as you are in school. That means you're getting your money's worth.
Right.
Okay, so let's look at where we had left off. So I'm inside of shunting yard. Oh, this is we were messing with. We actually never even got into shunting yard. We were messing with arrays and things like that. Okay, that's all fine and good. And what did we rate for our linked list so far? Then to string array. get. What did we do for string factory? Okay, string factory was a split function. Okay, did we write this yet? Was that one of our homework assignments?
Yeah, we did that.
Okay. So what you have now is you have an array of strings. So if I come down here, let's just get into driver CPP. All right, but it seems clear that we did not write that in class though, right?
I think we did a version of shunting yard. I mean, we had like the 2-string array portion and add end, and I don't know if that's what you were looking for, but.
Well, yeah, I mean, we were just building up the tools. That kind of corresponds to this slide right here. We're starting to build tools. So the very first thing we did is we need to split this guy up, and we got him into an array of strings, but we're ultimately going to want to put him in a queue of those tokens. We can store them as strings initially if we want. But it doesn't look like we actually wrote our split function in class. I gave it to you as a homework assignment, and then you had the exam that was due like by the end of that week because it was right before spring break. Since then we've gone over the exam, realized we hadn't talked about recursion, so we're pretending like we're post me giving the homework assignment for split. Does that sound accurate?
Yes.
Okay. Let me dump a bunch of this crap. And not going to use any of this stuff.
So we're going to be doing split for the next assignment, or?
We've already done split for the next assignment, but what you're going to do is you're going to augment split to get it into a queue. So for our next assignment, we're going to write a queue. So right now our split, let me come into, we did it inside this thing called string factory. And let me create a new file. We'll call this guy a queue.hpp. And he's going to include the same stuff as the driver. Let's see, who had string? Was that standard IO? Or is, no, it's IO string. It has to be IO string. Want to get it back to the right starting place. Split. Just comment this out for a second. Okay. So then our string factory, like this, and this was a static string pointer split from string factory. This guy takes in a string and a string constant as a parameter. Well, here, let me at least write in here what I want you to do. So you'll be able to take this as your starting point, and then I'll patch this up and push it so you have the right stuff. So update split to return a queue of strings that will represent our input queue for shunting yard. So right now you have this guy returning a string pointer. Ultimately, you're going to have it return a pointer to a queue, which means you're going to also have to write a queue. This will require you to implement a queue data structure that supports NQ and DQ. All right, that makes some sense. So we have our linked list thing here as a starting point if you want it, but we're actually probably not going to, we could probably say you can use that separately. So if I'm going to clean this out a little bit, I'd probably remove linked lists since we didn't really implement it out very much in here. So I'm going to get rid of linked list. I'm going to leave node because that'll help you in your queue. But we're going to have a queue and a stack. We don't need a linked list. So I'll do that. So I'll clean this up and get it to the point where it will at least compile as a starting point. I'll push it, and then the homework for next time is to modify your split function to return a queue of strings so that we have implemented the input queue portion of shunting yard. Does that make sense?
Wait, when you mean create a data structure, what do you mean by that? Like, is it like you're creating another method for it, or?
No, you're creating a queue. A queue is a type of data structure.
Right.
A stack is a type of data structure. A linked
Right.
list is a type of data structure. So you're going to create a queue.
Oh, okay. So you're going to create the CPP and the HPP.
Yep.
Okay.
To make a queue of strings, and you'll update your string factory to return a
Return those
queue from split.
Mhm.
All right.
Okay, that makes sense.
All right. I will see everybody on Thursday.
Sounds good.
And make sure you send me a message if you're having issues with any of your classes not meeting regularly or anything like that. That's important that we know what's going on so we can remedy that sooner rather than later.